Hi everyone. So we're going to talk about higher order derivatives today. And essentially what we're going to be doing is starting with a function, taking its derivative, and then taking the derivative of the derivative. Or perhaps taking the derivative of the derivative of the derivative, etc. Okay, so higher order derivatives, if you take the derivative of the derivative, that's called the second derivative. Or if you take the derivative of that, that's called the third derivative, etc. And when we start our next unit, which is called curve sketching, we're going to see how these higher order derivatives will tell us something about the graph of the original function. Okay, all right, so let's get into it. Okay, so if the original function is called f, or f of x, the derivative would be called f prime of x. The second derivative would be called f double prime of x. We'd use two dashes, and so on and so forth. Okay, so for example, find the first and second derivative of, f of x equals 8 root x minus 6x squared. Okay, so I'm just going to rewrite this as f of x equals 8x to the 1/2 minus 6x squared. Okay, so that radical has been written as a fractional exponent, and then I can now use my power rule to differentiate this. Okay, so the first derivative would be f prime of x is 8 times 1/2 x. Then I have to decrease that exponent by 1, so to the power negative 1/2, minus 6 times 2 is 12x. And then I am going to just simplify the first term. So 8 times 1/2 is 4. And then this negative exponent would come into the denominator, and that would be a radical square root of x in the denominator, minus 12x. Or if you wanted to, you could write it as 4 over x to the 1/2. That would be fine as well. So f prime of x is equal to 4 over root x minus x to the 1/2. And actually thinking ahead, I probably should have done that because we're going to take the second derivative. When we're taking derivatives using the power law, it's more helpful to have these fractional exponents written as exponents rather than radicals. Okay, so actually I'm going to do that and write this as 4 over x to the 1/2. I'll write both options, minus 12x. Okay, then when we take the derivative of this one, okay, f double prime of x, well, we have to think, all right, maybe if I take this guy and just think about what this would look like with a negative exponent, this term would be 4x to the negative 1/2. Okay, so if I take the derivative of that term, I would have 4 times negative 1/2 x to the negative 3 over 2. If I decrease that by 1 again, and then the derivative of 12x is just 12, so minus 12. Okay, and then again, I'm just going to simplify this first term. So the first term is going to become 4 times negative 1/2 is negative 2 over x to the 3 over 2. Or you could write it as the square root of x cubed minus 12, or f double prime of x equals negative 2 over x to the 3 over 2 minus 12. Okay, so this is okay. Whoops, I cut off the square root of x there. That's okay. That's okay. This is good, and this is good. Either form is fine. You can write the radical form or the fractional exponent form. Okay, you can keep going as well. So you could take a third derivative or a fourth derivative. After you find the third derivative, we don't keep writing dashes. We just write the number after the third one. Okay, so if you're writing the fourth derivative, you would just write f with a 4 in the superscript. Okay, so find the fourth derivative of f of x equals x to the 4 plus x. So we kind of have to go through all of them to get to the fourth one. Okay, so we've got to find the first derivative would be 4x cubed plus 1. And then the second derivative is going to be the derivative of what we just wrote above. So this is going to become 3 times 4 is 12, x squared. And then the derivative of 1 is just 0, so that term is gone. Third derivative is 2 times 12 is 24, so 24x. And then the fourth derivative, that's where we just write the number 4, is just 24. Okay, so there we have it. Okay, so essentially when we're finding higher order derivatives, we're just doing the process again and again. Now, where things can get a little bit more complicated is when we start doing higher order derivatives with implicit differentiation. So we're going to do a few examples of this as well. Okay, so we're going to start with this example over here. Y cubed equals 2x cubed minus 1. And we have to find y double prime. I'm going to use the dy dx notation when I'm doing implicit differentiation. And before I start, actually, I'm going to do something else, and you may wonder why I'm doing this right now. And what you'll see is that we'll come back to this in a little while, okay, in a couple of minutes. What I'm going to do is I am going to rearrange this function, or not function, but relation, to write it this way. Y cubed minus 2x cubed equals negative 1. Okay, so I'm bringing the x cubed term over to the other side. And we'll get back to that soon. Okay, all right, so the first thing we have to do is just take the first derivative. All right, so here we go. I'm going to start with the equation that we're given though. So d by dx of y cubed equals d by dx of 2x cubed minus d by dx of 1. Okay, and what I am going to get on the left side is, well, the derivative of 3y cubed is, sorry, not 3y cubed, y cubed rather, is 3y squared times dy dx equals the derivative of 2x cubed is 6x squared, and then the derivative of 1 is just 0. Okay, so all I have on the right side is 6x squared. And now I can solve for dy dx by dividing both sides by 3y squared. And so I'm going to get that dy dx equals 6x squared divided by 3y squared. 6 divided by 3 is 2. So this is going to become 2x squared over y squared. Okay? So that is my first derivative. Now, to get my second derivative, I have to take the derivative of both sides of this equation. So to get the second derivative, that's what I'm going to do. Okay, so I'm going to do this. D by dx, or d squared y, this is the notation that we write, by the way, by dx squared, is going, for the second derivative in dy dx notation, it would be d squared y by dx squared. If we took the third derivative, it would be d cubed y by dx cubed, etc. Okay? Sorry, I should have mentioned that before I just went into it. But here we go, is going to equal on the right side, d by dx of the right side, which is 2x squared over y squared. Okay, and the reason, by the way, I kind of skipped ahead a little bit, but the reason why we have this d squared y by dx squared is because what I'm doing here is I'm going d by dx of, dy dx of y over dx. Okay, so that's where this d squared y by dx squared comes from. Okay, so anyway, let's go ahead and do this. Okay, now what we have to worry about on the right side, luckily the second derivative has been isolated because the first derivative was isolated. What we have to worry about on the right side though is taking this derivative, and what we've got here is a quotient law. Okay, so we have to think, okay, what's u, what's v, and what's u prime, what's v prime. Okay, so in the numerator I've got 2x squared, which means u prime is 4x. In the denominator, I've got y squared, which means v prime is 2y times dy dx. Okay, so now I'm going to put in my quotient rule to take the derivative of the right side. Okay, so I'm going to get, let's see, u prime v, so u prime is 4x, v is y squared, minus uv prime, 2x squared times 2y dy dx over v squared, y squared squared. Okay. Now I'm going to simplify this a bit, and the other thing that I can do is I have an expression for dy dx in terms of x and y. So what I can do is I can take this and sub this in for here, for this. Okay, so that's what I'm going to do on my next line. And we're going to continue this up here. Okay, switch back to black. All right, here we go. So what do we have? We've got 4xy squared minus 4x squared y, because 2 times 2 is 4, so 4x squared y, and then dy dx was equal to 2x squared over y squared, so times 2x squared over y squared over y squared squared is y to the 4. Okay, and now I can simplify the numerator even more, because in my second term, one of the y's, this y in the numerator over here, is going to cancel with one of the y's in the denominator. So this is going to cancel with one of those. And then I've got this y in my denominator in one term. If I want an LCD between these two terms, this denominator right now is 1. So I need to multiply this by y over y. And then I'll have an LCD between those two terms in the numerator. And what I'm going to get is, let's see, so 4xy squared times y is 4xy cubed minus 4x squared times 2x squared is 8 x to the 4 all over y over y to the 4. Okay, and now there's two things that I'm going to do. Firstly, I can bring this y down into the denominator. And secondly, I can factor the numerator because I've got a common factor of 4x in the numerator. So I'll factor that out. And I have, let's see, 4x times y cubed, that's in the first term, minus 2x cubed, that's in the second term, over, and now I have y to the 5 in the denominator. Okay, now let's go back to the first thing that I did, which I said I was going to come back to, which was I, over here, took this piece and I brought the 2x cubed over to the other side so that one side was equal to y cubed minus 2x cubed and one side was equal to -1. And what you can see here is that my factor, one factor is 4x and the other factor is y cubed minus 2x cubed. So because that's equal to -1 in the original relation, I can actually now go back and replace that with the -1 in my second derivative. So that's what I'm going to do next, and that will simplify things quite a bit. And finally, what I'm going to get is 4x times -1 over y to the 5. So the final answer for the second derivative is d squared y by dx squared is -4x over y to the 5. And there we go. Okay, so there were some fancy substitutions. I would say that I would definitely expect you to do the first one where you substitute in 2x squared over y squared for dy dx. This second one is some fancy gymnastics that you have to do, right? Because you have to recognize that, you have to isolate the -1 initially. And that's quite advanced, but I would definitely expect that you can do the first substitution that we did to substitute in for dy dx. Okay, so we're going to try one more and that'll be it for today. Okay, this one also is an implicit differentiation example. Here we've got x cubed plus y cubed equals 5. So we're going to start out exactly as we did with this first implicit differentiation, where we're going to find the first derivative. So let's do that. Okay, so here we go. So we're going to go d by dx of x cubed plus d by dx of y cubed equals d by dx of 5. Okay, and d by dx of x cubed, derivative of x cubed, is just 3x squared, plus d by dx of y cubed, derivative of y cubed is 3y squared rather, times dy dx, equals derivative of 5 is just 0. Okay, so now to solve for dy dx, I've got to bring the 3x squared over, so I'm going to subtract that from both sides, and I'm going to get 3y squared times dy dx equals -3x squared. And then to solve for dy dx, I have to divide both sides by 3y squared, so the 3's are going to cancel, and I'll get dy dx, my first derivative, equals -x squared over y squared. So there's my first derivative. Okay, to get the second derivative, okay, I'm going to take the derivative of both sides of my first derivative. Okay, so I'm going to go d by dx of dy by dx equals d by dx of -x squared over y squared. And just like we did above, we've got another quotient rule. So I think just because I have some space over here and we're getting a little crammed, I'm going to write out my u and my v and my u prime and my v prime right in this little box over here. So in my numerator, I've got -x squared, so u is negative x squared. So that means u prime is negative 2x. V is y squared, which means that v prime is 2y times dy dx. Okay, so now I'm going to go up here. Probably should have given you guys more space for this one. And I'm going to differentiate the right side using the quotient law. So that is u prime v minus uv prime over v squared. Okay, so u prime v is negative 2x. V is times y squared minus uv prime. So negative x squared times 2y dy dx over v squared, which is y squared squared. Okay, and what we want to do, just like in the last example, is we want to substitute in negative x squared over y squared for dy dx. So I'm going to do that right now. So I'm going to take this and stick it in here, because that's what dy dx is equal to. All right, so let's go. And then basically we're going to do some simplification. All right, so this is negative 2xy squared. And then we've got negative x squared times 2y. Okay, so plus 2x squared y times negative x squared over y squared over y to the 4. It's looking quite similar to the last one. And again, on the right, in the second term in the numerator, there's one y that cancels over here with one y in the denominator. So the denominator, the LCD rather, between the first and second term in the numerator is y, because this right now is over 1. So if I want an LCD, I've got to multiply this by y over y. Okay, so let's do that, and we're going to get negative 2xy cubed. And then let's see what we have here. Okay, so negative x squared times 2x squared is minus 4x to the 4 all over y over y to the 4. Okay, and similar to what I did in the example above, I'm going to bring this y down, and I'm going to factor the numerator. And in the numerator, there's a common factor of 2x, and I'm also going to factor out the negative sign as well. So I'll bring the LCD out as negative 2x, and I'm left with y cubed plus x cubed over y to the 5. And what you might notice is that in the original relation, x cubed plus y cubed equals 5. So I can substitute a 5, since it's equal to x cubed plus y cubed, for this factor. I can sub in a 5. Okay, and that's going to make things a lot nicer. I'm running out of space here. Let's see, let's go up here. Okay, so equals negative 2x times 5 over y to the 5. Okay, so all together, d squared y by dx squared, that's the second derivative, equals negative 10x over y to the 5. And there we go. We have just taken the second derivative using implicit differentiation. And that is all that I have for you guys today. I'll see you guys soon.